and this will be for capacitive elements and inductive elements. We're looking for, and you're probably well aware of some quantities that are equivalent to resistance that we've been using when we had DC circuits only. Basically, what we are looking for is something like this, where we have a quantity called reactance. Now this is my definition of what reactance is, and there is capacitive reactance and inductive reactance. That is, and those are indicated by X, usually capital X, with a subscript of either L or C, for L for inductance and C for capacitance. And you've probably learned in physics that X sub L is equal to omega L, or 2 pi FL. And X sub C is 1 over omega C, or 1 over 2 pi FC. So basically, this stuff is probably not new to you. You've probably seen it before. That's fine. Here's a quick example where we are talking about setting an omega equal to 100. We have a 1 Henry inductor and a 20 microfarad capacitor. What is the X sub L? The X sub L works out to, we put 100 in here for the omega and 1 for the inductance, and we get 100 ohms, as we would think. And for the capacitor, 100 times, and for the capacitance, it's 20 microfarads, so that's 20 times 10 to the minus 6th. When you plug those values in, you will get 500 ohms for the X sub C capacitive reactance. So there is another quantity that has to do with the restriction of current, and it is called impedance, and that is capacitive and inductive again. Now, once again, I will say that this is my definition, and I have to tell you that I was trained in the early 60s a little differently from what people I see in textbooks these days, and as a result of that, I've never been able to fully recover, so I've had to come up with my own ideas as to what the differences between reactance and impedance as it applies to a single component like a capacitor or an inductor. So what we have here is, and I'm calling this Z sub L. It's designated with a Z, capital Z usually, for inductive impedance and capacitive impedance. And again, and as you can see, the major difference between the two is that now we have the complex version of the restriction on current, and this is the one that we actually will end up using. It would be obviously J omega L and 1 over J omega C for the capacitor. So J omega L for the inductor, 1 over J omega C for the capacitor. And if we do this same kind of calculation, plugging in values with the same starting numbers, we get a Z sub L of J 100 ohms and a Z sub C of minus J 500 ohms. So why the minus J? Well, it's mainly because when we do a calculation, remembering that J is the square root of minus 1, if you have a quantity that is hold on here, okay, if you have a quantity that is labeled 1 over JA, we'll just call it A for right now, you've got an improper fraction, right? You've got a square root in the denominator. Generally, you want to rationalize that so that and the way you do that is you multiply numerator and denominator by that square root number. So j over j. So now this gives you j over j squared a, but j squared, since j is the square root of minus 1, that's a minus 1. So it's j over minus a, or you might say minus j, and I'll make that dot, okay, times 1 over a. So that's how you get the minus sign. So just to make sure you get that part, so this is the end of the definitions of the AC restrictions on current. So what happens when we add resistance to the circuit? We want to add resistance because we've only been talking about the capacitor and the inductor. So when we do that, the circuit might look something like this, where you have a generator here, some sort of AC generator, and that's what the little squiggly line is meant to show, is that it is an AC, it's supposed to represent a sine wave, so it's AC, and we have a resistor and an inductor in series. So how do we add those together? Well, just like we add series resistances. So we have a total impedance now, because of the inductor in there, we have an impedance that's R plus Z sub L. But Z sub L, as we remember, is j omega L, so this is a complex quantity that we have here, R plus j omega L. And so we can show how that plots in the complex plane. Here we are. We have the resistance, obviously, along the x-axis, and we have the impedance, the inductive impedance, along the y-axis. And the total impedance is the resultant of those two, the resistance and the inductive impedance. And so this would be Z total right here. So now you can see that if you talk about the Cartesian coordinate system or rectangular coordinates, it would be R plus j omega L. Then also you could say that the Z total has a magnitude and an angle that would be in the polar, represented as a polar, in the polar space. And so it would be R theta space. So that is basically the way you've dealt with complex numbers in the past. And so we're going to continue doing that here because it does make things a little simpler. It certainly is good because it keeps us out of having to solve differential equations. And so that's why we're going with complex arithmetic here. And I just remind you once more that we're talking add, subtract, multiply, divide. That is arithmetic. It's not calculus or anything like that in the complex world. We're just talking those four operations, plus obviously converting from polar to rectangular or back.